the degrees of freedom is more than 100, you can use that table. Although you're working with t distribution, so you have to write t stat. But probability wise, you can still use that table because the numbers are so close. Right? I know in B11 they keep saying 30. Is it 30? They say the sample size more than 30. You can see that probably is not correct. Check the numbers when you have a 30 degrees of freedom. Check 30. 2.72 versus Z of 2.5 is a big difference. That's like big difference. The tails are way different. They're way different. The tails are way different. So you should not use Z instead of T unless the sample size is really large, i.e. degrees of freedom is really large, more than 100. That's what we did, right? Don't use 30. You make errors, right? Everything will be off by 10, 15% if you do. If you cross 100, the difference will be negligible. It's fine. This is not a big difference. Close. Make sense? Anyway, that is t-table. Using t-table is problematic because we don't have all probabilities. If we don't have all probabilities, then we are fine if we use rejection method. If you have the probability of interest. You will test at 5, 10, 100% and so forth, they're all given there. But if you want to do p-value method, then the table is not very good. We cannot calculate p-value because we don't have all the probabilities. The only thing we can do is approximate p-value. That's the only difference. Otherwise, everything works. Say we are doing this test. We are doing this test. Let me open the page. Suppose you are doing this test. Let me give you an upper tail test first. That is the null, that's the alternative. You took a sample, that's a sample mean. That's not the mean. Right? Which makes this the correct test, because as we know, the sample mean, which is your evidence, is for the alternative, which is fine. If this was less than 100, that would have been the wrong test. There is no evidence for that test. So we're fine. The sample size is, say, 64. I don't know if 64 is on the table. Let's make it 50. So let's make it 51, so we are sure the number is on the table. We need to calculate our t-stat, which will be the evidence standardized by the null. Suppose S is 12, that would be 12 square root of 12. That is our t-stat. Degrees of freedom is 50, which is n minus 1, that's a degree of freedom. What is t-stat in this case? What's the t-stat? What is standardized t? That's the t-stat. What do you get? I think you get a big number.
2.98.
2.98. So I'm going to do two tests with two different numbers. I'll tell you why. Suppose this one was 1 or 2. Get me the other one. What's the second one? Two different tests. With 105 evidence, that's a t-stat. With 102 evidence, that's a t-stat. What do you get just for the second one? How much? 1.18? Okay, so let's start with this one. The alpha is not even. We know alpha there, right? Make sense? The alpha is not even. We want to find p-value. How do you find p-value? That is our t-table. That's the degrees of freedom. Right? For a degrees of freedom of 50, C of 10% is 1.299. Right? On to the left of this one, what does it mean? Bravo to us. That's 1.299, I get 1.18, right? To the left of this one. The probability will be higher than 10%, lower than 10%.
Higher.
Higher, so the p-value is higher than 10%. If you fall to the left of the highest one, the p-value will be higher than the highest one. So based on that, I conclude p-value is more than 10%. That's for the 1 or 2. Right? Make sense? What about this one? What about this one? So, my evidence 102, my t-stat is 118, which is lower than the lowest on the table. The p-value will be higher than the highest, which is 10%. It will be more than 10%. That's what I can say. What if we get 2.98? Higher than this one. Make sense? This is 0.5%. Right? So what would be the p-value there? Lower than 0.5%. That is lower than 0.5%. I made the numbers up. I made them up. But I didn't end up with between two numbers. In one I ended up with lower than lowest, and the other one I ended up higher than highest. So the rule of thumb is simple. If you end up lower than the lowest, the p-value is higher than 10%. If you end up higher than the highest, the p-value is less than 0.5%. Right? Let me go to another one. What if the evidence was, let me use a different color, 103. What's the t-stat then? What do you get now? Suppose the evidence was 103. What would you get for the t-stat? 1 point? 1 point? 79? 1.79. I think it will fall between two numbers. That's what they wanted. 1.79. That's 50, right? Between these two. The p-value will be between these two. So, simple rule of thumb. Although you cannot calculate the exact p-value, you can range bound it. You can find the range for it, right? Check t-stat. If it falls between two numbers, that's the range of p-value. If it's higher than the highest, the p-value is less than 0.5%. If it's lower than the lowest, the p-value is higher than 10%. Make sense? That's the p-value. The test is 1 second. Right? So in this case, for that, I'll fall between these two numbers. The p-value between 2.5 and 5%. That is my conclusion. Right? Make sense? So although you cannot find the actual p-value, you will be able to range bound it. Alright? Find t-stat, check the table, in between, that's the range of p-value. More than the highest, the p-value is less than 0.5%. Lower than the lowest, the p-value is more than 10%. Right? Let's go through another one. Just another one. You are doing this test. Two-sided. That is your null alternative. Now that is the evidence. 57. Right? That's your evidence. N is 36. S is 10. Right? Make sense? Okay. Alpha is given at 5%. Alright, do this task using both rejection method and p-value method. Let's say we typically don't do rejection, just as an example. I give you the alpha, I want you to use both methods to do this test. Right? Make sense? Okay. I check out. I don't have sigma, I have S, that's a T stat. I calculate T stat. It would be having degrees of freedom of 35 and minus 1. And it would be 57 minus 60, 10 square root of 36. What is your T stat? There will be a negative number here.
Minus 1.8.
Minus?
1.8.
Minus 1.8? Like this? Similar to Z, T is symmetric. You can ignore the sign. Look at the upper side and answer the question. It's symmetric distribution. So ignore the sign. Find T 2.5% from the table. Two-sided split the alpha. Fine? Make sense? This is step number 2. This is step number 3. I'm doing step number 3, 1. I'm doing rejection method. I need the rejection value from the table. Right? Check T of 2.5% with degrees of freedom of 35. Yeah, ignore the sign because the distribution is symmetric. What is T of 2.5%? 2.03. 2.03. Is it 2.03? 1.8 is less than this one. Do not reject. That's it. I do the same thing as before. I ignore the sign. Check the number from the table. Less you don't reject, more you reject. Here, this is less, I don't reject. I could have used the sign. So that doesn't do anything. I could have used the sign says the rejection value is less than this one, minus 0.8 is higher than that one, I don't reject. I could have done it that way too, but it's easier to ignore the sign because it is symmetric. Alright, then use more you don't reject, more you reject, less you don't. Make sense? If you ignore the sign. Anyway, so here, I do not reject the null because the rejection value is 2.03 and I got 1.8. I use the absolute values. Right? I could have said, with the number, this is my critical value, minus 1.8 is more than, don't reject, the same conclusion. I could have used the sign as well, and done it, but if you ignore the sign, that's easier. The distribution is symmetric, it runs both ways. Okay, that is 3.1 rejection method. What about the p-value? Check 1.8, again, ignore the sign. See where you fall in between. Right? Similar to one side of the test. So go there. Go there. That's 35. Where does 1.8 fall in between? It falls between these two. Right? So what's the p-value? What's the p-value? 35, it falls between these two. What's the p-value? Is it 2.5 to 5? No, that's for one-sided test. For two-sided, you double it. That's the only difference. So the same thing that you did for one-sided holes here, but when you find the range of probability from the table, you double it then. So the p-value here is between 5 to 10%. T stat, ignore the sign, see what you fall in between. That gives you a range of p-value for one-sided test, for two-sided double. Make sense? Okay. Anyway, question for you. Why they call it degrees of freedom? You know, T distribution is characterized by degrees of freedom. In this case, degrees of freedom is n minus 1. Why? Why do they call it degrees of freedom anyway? Anyone? Yeah?
This is a guess, but for example, if you have a mean that we have calculated, there are many different, numbers when we add them up. And all those numbers could be, specific things, but then the sum divided by the n.
Yes, that's correct. Is how free in selecting the sample. So you're basically saying, if I want to select a sample of n minus 1 I'm free to select. The last one I'm not. The last one is set because I have a restriction. So technically, degrees of freedom is sample size minus the number of restrictions you put on the model. In this case, you have one restriction. Why that's the case is a different story, but if you want to calculate S, you have to have X bar to calculate it. That's one restriction. Later on, you see in other models, you may have more restrictions. So degrees of freedom might be n minus 10, minus 20, depends on the case. Degrees of freedom is n minus the number of limits on your sample selection that you have. So in this case, you have one limit. That's the idea. Make sense? Anyway, they call degrees of freedom because that's the freedom of selecting items in your sample. You are free to select all of them except the last one. That's n minus 1 degrees of freedom. N minus 2 basically means you're free to select all of them except the last two. Make sense? And so forth. Anyway. So T is not characterized by n minus 1 as a degrees of freedom, it's characterized by degrees of freedom. Degrees of freedom depends on the application. It might be n minus 1, which is this one. Later on, might be n minus 2, might be n minus 10, depending on the case. Right? Okay. So let's see where we stand. We are there. We'll finish this one. Item 4. Confidence interval, you learned it in B11. Alright? If you want to calculate confidence interval, you have a point estimate. That is your sample statistics. For the mean, that's X bar. For the proportion will be P bar. Later on, for the variance will be S squared. But what you get from the sample, that's a point estimate. The up and down, that's the margin of error. Alright? Make sense? So for the mean, which we care about for the time being, you have a point estimate, which is your X bar. That is your point estimate. Right? Make sense? The up and down is called margin of error. Right? This is ME, margin of error. The margin of error is subject to two things. What are those two things? I'm pretty sure you did it in yellow. What are two things that decide the margin of error? First, your confidence level. That's 1 minus alpha, your confidence level. That decides your Z or T depending on the case. Right? Multiplied by standard error. So you have confidence interval, that's the point estimate. The up and down depends on two things. Standard error. If you have the population version, you use Z. If you have the sample version, you use T. Right? Make sense? Say, so now we can write like this. Probability of falling in between the ranges 1 minus alpha. That's sort of what I write. That's the up, that's the down, that's the center of the confidence interval. So anytime you have confidence interval, right in the middle is your point estimate. The up and down is subject to confidence level, which decides Z or T depending on the case, standard error. Right? If you increase increase your confidence, what happened to the confidence interval? If you increase one minus alpha, decrease alpha, what happened to range? This will go up or down. If alpha comes down, will this go up or down? Will be higher. Z of, say, 5% is lower than Z of 2%. Make sense? This becomes higher, this becomes bigger, the range becomes wider. The more precise you become, let's have it backwards. More confident you become, less precise you are. If you increase this one, the range becomes wider. Make sense? If you decrease this one, the range becomes narrow. Sort of obvious. I can say I'm 100% confident. On test 1, the average will be between 0 and 100. Very confident, but I'm not precise at all, right? The more confident you become, less precise you are. There's a trade-off between these two. Right? You have a wider range, the more confident you are. You have a narrow range, the less confident you are. That's sort of what we do. Say you take a sample, the sample mean is 150. Say, right? S is 10. Right? N is 41. Right? What is 95% confidence interval for the population mean? Yeah, since I don't have sigma, I should use T to build it.